Hey everyone, and welcome to today's Explainer. We're jumping right into a really fascinating journey today. We're going to explore exactly how machines perceive the physical world around us. And to do that, we're going to look at two radically different ends of the spectrum. I'm talking massive landscape-level spatial scanning on one end and microscopic, hyper-fast manufacturing on the other. It's a tale of the macro and the micro, and I am so excited to guide you through it. Let's get into it. So think about this for a second. How does a machine map a vast outdoor canyon versus perfectly aligning a single toothpaste tube on a factory floor? Just think about the sheer difference in scale there. One task spans kilometers, right? It deals with mountains, trees, blinding sunlight. The other task, well, that deals with fractions of a millimeter on a glossy piece of plastic moving at lightning speed. It really seems like these two tasks would have absolutely nothing in common. But actually, here's the secret connection. Whether we're wrapping a dark forest from an aircraft or detecting tiny cut marks on a colorful film wrapper, it's fundamentally all about the same thing: interpreting reality through bouncing light and waves. Engineers simply adapt the machine's eyes, the sensors, based on the specific scale and environment of the task. That core problem-solution arc is exactly what we're going to unpack today. Okay, Section 1, Sensing the Modern World. LiDAR, Pulse versus Phase. Let's start with the macro scale and dive into the two absolute titans of LiDAR technology. Just so we're all starting on the exact same page, let's quickly establish a baseline. LiDAR is a remote sensing technology. Basically, it measures distance by targeting an object with a laser and analyzing the reflected light or waves that bounce back. It's essentially throwing out a beam of light, waiting for it to hit something, and measuring what comes back to understand the 3D space. Pretty straightforward, right? But not all LiDAR is created equal. We have an immediate dichotomy in the technology here. On one side, we've got time-of-flight LiDAR, which boasts massive ranges of over 1 kilometer, but it operates at a moderate speed. And on the other side, we have phase-shift LiDAR. Now this has a much shorter range of about 300 meters, but it operates incredibly fast. This brilliantly illustrates how different environments require completely different engineering trade-offs because, well, you can't always have maximum range and maximum speed at the exact same time. Let's break down time of flight, or TOF, first. Think of this technology as the ultimate macro-level eye. It works by measuring distance via pulse timing. It literally times how long a single laser pulse takes to go out and bounce back. Because of this method, it can achieve those incredible ranges of over a kilometer. It's also highly sunlight resistant and multi-return capable. That means a single pulse can hit a tree canopy, register the leaves, and still bounce off the ground below. If you're doing outdoor, topographic, or forestry scanning, this is hands down your go-to tool. Now, in contrast, phase-shift LiDAR measures distance a bit differently. Instead of single pulses, it analyzes the phase differences in a continuous wave of light. And because it's continuous, it captures data very, very fast. We're talking high point density and excellent accuracy. The hardware can also be a lot more compact. However, there's a catch. It is sensitive to sunlight and usually only provides a single return. But that makes phase shift the absolute champion of indoor hyper-accurate mapping. It's perfect for architecture, industrial measurements, and creating digital twins of indoor facilities. All right, Section 2, Contrast Sensors in Automation, the microscopic pivot. Buckle up because we are making a hard pivot right here. We've just mapped a kilometer-wide canyon, and now we're zooming all the way in. We're moving from surveying drones way up high right down to the factory floor. We're leaving the massive, wide open world and entering the hyper-fast, millimeter-precise reality of automated packaging. But I really want you to remember this. We are still applying those exact same light-bouncing principles we just talked about. It's just scaled down to an incredibly tight, incredibly fast environment where margins of error are practically non-existent. I want you to focus on this single number, 50. In the world of industrial packaging, 50 microseconds is the response time of the Luz KRT3C contrast sensor. To a human eye, 50 microseconds is completely invisible. Literally, it's a fraction of a blink. But to this sensor, that's plenty of time. That is how fast this machine needs to see, process, and react to a target flying past it on a conveyor belt. Now, what's really interesting here is the sheer data density packed into such tiny hardware. It's incredible. Looking at these two low-ISO contrast sensors, the KRT3C is just 11 by 32 by 17 millimeters. That is roughly the size of your thumb. Yet it's firing it up to 10,000 hertz with a highly precise operating range, hovering right around 14.5 millimeters. In automation, you gotta remember, factory space is premium real estate. Sensors absolutely must fit into impossibly tight machine spaces while still delivering this massive performance. Section 3, Industrial Light and Color, matching the tool to the target. And this brings us to a really fascinating challenge in microscopic sensing. Just like LiDAR had to choose between pulses and continuous waves, these microsensors have to choose the right color of emitted light to reliably detect a contrast marker. Depending on what you're manufacturing, the physical target changes. These loose sensors use 3 distinct light types to conquer this. Multicolor, or RGB, automatically selects the best color to detect contrast on very colorfully printed films. But if you're dealing with highly reflective glossy surfaces, white light provides unmatched reliability. And if your target is microscopic, or if the distance to the target changes even slightly as it moves, a red laser gives you a tiny, hyper-focused spot. So a single packaging machine might actually need to switch between these, depending on the exact product being run. To anchor this in reality, just imagine a plastic tube of hand cream. Before the machine crimps and seals the bottom, a contrast sensor uses light to find a tiny printed mark, ensuring the tube is rotated perfectly so the logo faces forward. Or think about a thermoforming machine pumping out plastic trays. A sensor is constantly watching for a specific tape splice that indicates the endless roll of film is running out, that prevents the whole machine from jamming up. I mean, that is what these sensors do all day, every day. And here's the thing. They don't just do it in pristine, clean laboratories. Factory floors can be brutal. These sensors carry an Ecolab certification, alongside IP67 and IP69K ratings. In plain English, that means they are entirely dust-tight and can survive being blasted with high-pressure, high-temperature industrial cleaning agents. And they just keep right on working. They are every bit as tough as they are fast. Section 4. Teaching machines to see. Calibration at high speed. Which leads us perfectly to the human element of all this automation. How do engineers actually program a 32mm piece of plastic to recognize a contrast mark passing by in 50 microseconds? Well, getting these sensors ready involves specialized teach modes and a technology called I/O link. So the crucial point is this. If a factory changes from packaging chocolate bars to packaging mints, the calibration of these sensors must be incredibly easy and fast. If it's complicated, the factory suffers super costly manufacturing downtime. One of the most brilliant ways this is handled is through the dynamic 2-point teach mode. Imagine a conveyor belt that is actively running. You don't even have to stop production. The operator simply presses a button to open a measurement window. The sensor watches multiple contrast markers fly by on the running belt, learns the difference between the mark and the background completely on the fly, and then the operator closes the window. That's it. The sensor has taught itself its new environment in real time. Now let's see how this builds with an alternative method, the static 1-point teach. This is particularly used on the white light KRT-18B models. Here, the conveyor belt is completely stationary. You align the sensor with a plain blank background, you teach it that background. From that moment on, any signal deviation, literally anything that breaks that homogeneous background, is instantly detected as a marker. It's a highly reliable way to find anomalies. But the true magic of modern automation is I/O link. This is the communication standard that takes these sensors to the absolute next level. Because of I/O link, operators can use what's called recipe management. If the machine switches from the chocolate bar film to the mint film, the central control system instantly uploads the new parameters directly to the sensor. There is zero manual reteaching required on the factory floor. It also offers real-time condition monitoring and even lets managers remotely lock the physical buttons on the sensor so no one can mess with the settings. Talk about a real game changer. From LiDAR systems mapping kilometer-wide forests with laser pulses, all the way down to microscopic sensors using white light to perfectly align a toothpaste tube in 50 microseconds, the way machines interpret our physical reality is advancing at a staggering pace. So, I'll leave you with this. What does our future look like as the sensors mapping our world and manufacturing our goods become even smaller, faster, and exponentially more intelligent? Next time you hold a perfectly sealed product, take just a moment to appreciate the invisible, high-speed choreography of light that made it possible. Thank you so much for joining me on this explainer, and keep learning.